Hello, my name is Ryan Howe, and today we're going to be using Young's double slit experiment to find a laser's wavelength with experimental values. So what does the setup look like? Basically, we have this laser. Here it is right there. I'll draw it on the screen. It's going to be shooting a laser out of it through a slit. You can see the slit somewhat right here. And the slit's basically going to look something like this. It's going to have two holes through it. And then another board right there. And then the screen right here will have the screen, and the image will be projected. You can think the screen will be very, very far away compared to the magnitude of this of the slit distance right here. So let's find our values. What do we know? Basically, we found the width of the slit measured using a vernier caliper. And let's zoom in to see what the value is. From this, I can see basically how to look at this is to see how far away this value is from here. So you can see this is a 1 centimeter value, so each of these are going to be 1 millimeter. I can tell it's a little bit between the 0 and the 1 millimeter, and I'm just going to go ahead and say it's about 0.4 millimeters. You could disagree, maybe you could say 0.3, 0.5, but it doesn't matter too much. It won't get us off too much. Then the next part is diffraction grading. The important value is to get the distance to the first maximum. So we can see that this main spot right here, we put our centimeter here, and we can kind of see the main bright spot. The center is right there, and then we have to find where is the next bright spot. And I can kind of tell it's right around here, right around there. So I'm going to go ahead and draw that down. And to me, it looks like it's lining up about around 1.2 centimeters. So some of the other values, these are kind of givens that we started the experiment with. The distance from the slit to the wall was measured as 4.8 meters. The height of the laser is 1 meter above the ground. A fair warning, this won't actually come into play, so that isn't too important. And then the slit width, what we just found was 0.4 millimeters, and then the distance to the first maximum is 1.1 centimeters. Instead of 1.2. So I had a slightly different value. And then let's convert. Basically, we want to have all our values in the exact same dimensions. Like we want to have them all in meters, because we have a meter here. It's actually, you just have to have them all in the same metrics. Because we have 2 meters, I think the best way for us to approach this, the easiest way would be to just convert them all to meters. So we already have these top 2 as meters, and then the slit width is 0.4 millimeters. We can use dimensional analysis to solve this. Basically, we say how many millimeters are in 1 meter. And I think it's 1,000 millimeters in 1 meter. So we can put 1 meter up here. Basically, the millimeters here will cancel out millimeters here, and it will get us so 0, 0, 0, 0. This point will go back quite a few places. So originally we'll have the 4 here. Originally the point was right here, so we'll go back 1, 2, 3, 4. Now, so that means it's going to be it's going to be 0.0004 with 4 zeros. And then we also have to find the distance of the first maximum. The first maximum is 1.1 centimeters. We'll use dimensional analysis again. How many centimeters are in 1 meter? There's 100 centimeters in 1 meter. So we'll do this. We'll say centimeters and centimeters cancel out. What's 1.1 divided by 100? Basically, all we have to do is put this dot back 2 places, and we get 0.011 meters. And it's good. This is also in meters, so we can put meters right here. Awesome. So now we got all our values, and now all we have to do is what formula can we bring in? We are trying to relate the distance from the slit to the slit width and distance to the first maximum. So an important part in AP Physics is identifying our values, so then we can basically find a formula. We are trying to find the wavelength lambda, so we need to find one formula that only has those values and relates all of them to each other. It turns out this formula here, A times y min over L equals m times lambda. The A is the aperture. This sounds like a big word, but it's actually just the slit width. So it's just the distance between the holes in the in our slit. So it's just that distance there to there is A. And then what is our y min? Our y min is the distance to the first maximum. So in our previous example, we had the picture of all the different, we had this bright spot here, and then we had another bright spot here, and it basically just keeps going on and on and on. But all we're looking for is this main bright spot to the first, the center to the first bright spot. And then the L is the distance from the slit to the screen. So how far is the board that we have, the whiteboard, going to be from the slit that we had? And then M will just be 1 since we are only finding the distance from the first maximum. Sometimes you could have an M of 2, but then you need to measure the distance of the next bright spot. Instead of finding this value of y min, you would need to find y min of the second one. So we'll only be using this one right here, since that's the y min we measured. And then lambda is the wavelength, which is what we were trying to find. Let's solve for the wavelength. Now we know all our values. We can basically just plug it into the formula. Since m is equal to 1, we don't even have to rearrange the formula to solve this. We can just say A times y min over L is equal to lambda. What is A? The slit width, the aperture is 0.04 meters. So we can plug in 0.00, I think there's 3 zeros, and then times y min. What is y min equal to? Well, y min is just the distance to the first maximum, and it looks like that's just 0.011 meters. And then this is all over L, and L is the distance from the slit to the wall, which is 4.8 meters right up here. So we'll plug that into our equation, 4.8 meters. This is also expressed in meters. We'll just put an M right there. And then we can just plug this into our calculator. We pull out our calculator. We plug in 0.0004 times 0.011, and we press enter, divided by 4.8 meters. And we basically get, I get 9.166 repeating, and we just round that off to 7 here. And then we set that equal to lambda. What will the units be? That's an interesting question here. Basically, we just see that there's a meter here and there's a meter here, and that the meter is dividing, so they basically just cancel out. So that'll just cancel out, and it will just give us meters. So lambda will be in meters, which is good because lambda is usually expressed in meters. So we get this value of 9.1667, and I forgot to add, this is 9.1667 times 10 to the negative 7. So the next step here is to convert to nanometers. Because wavelength is usually expressed in nanometers, it's not usually expressed in meters. So we got this value of 9.1666 repeating. It's important not to round this till the very end of the process to avoid intermediate rounding error. So we can say this is, right now this is in meters. So this is times 10 to the negative 7. And then we have to ask ourselves, we have 1 meter here. How many nanometers are in a meter? That's 1 times 10 to the 9 nanometers. We can multiply our number that we originally have here back into our calculator times the 1 times 10 to the 9. So I'll just multiply our value times 10 to the 9, and we get 916.66 repeating nanometers. So that equals lambda. An important part here is to think back originally, what are the values we're plugging in so that we know the significant figures? Well, when we were looking at our vernier, our caliper, we were using this value that was, I'm pretty sure, was 0.4 millimeters. This only has 1 sig fig. We couldn't really get too much of a better approximation. So our answer can only have one sig fig. So I can round this off to 1,000. I'll say this is approximately 1,000 nanometers. So that's approximately equal to lambda. Okay, let's look at situations where our methodology may not work as well. Let's look at Fresnel versus Fraunhofer diffraction. So Fresnel diffraction is basically when, let's say you have a slit, and it's just super, super close to the screen. It's like nanometers close. It's not, the waves aren't going to have a chance to really interfere with each other and create the diffraction that we're looking for, and our equation wouldn't really apply. The one that we're used to is the Fraunhofer diffraction. This is one we're using, and this is the only one that it would work for. Basically, with Fraunhofer diffraction, we can derive our formula. Let's say we have this screen really, really far away. You could say it's all the way over here, and there's this point like about right here. You could basically say that these are parallel to each other. Let's just say, I won't draw the screen because it's kind of impossible to draw how far away the screen would be in this PowerPoint at least. Basically, we have these two rays, and they're basically parallel. It would be because the legs are so big, and theta's probably pretty small. It would be a very small value also. So that's why the legs are kind of basically parallel to each other. So when we try to solve for this, we can set this one line. This is kind of like the line that crosses over. It's kind of just straight across. It's going at the slit with a 90-degree angle. It has another line here that's also parallel. So it's also parallel. It's also hitting that point. It's approximately parallel. And we find out that this angle here, we'll define this angle as theta. It turns out this angle, if we do a 90-degree angle right here, turns out this angle here is also theta because of this parallel effect. And this is a reason that we're able to derive our formula. We could basically say this is the change in x, this is the aperture, this is the y min, so you could think the point would be right here. That would be the y min, and then the length, interestingly enough, is equal to the hypotenuse when it's such a far distance. You could basically say they're equal to each other because the points, theta is just going to be so small that it won't really matter too much. So you could basically say this length here of this long segment here is going to be equal to L. So now we can relate it by sine of theta. We could say, hey, we have two places where we can find sine of theta. We can look, hey, there's sine of theta right here. Sine of theta is just opposite over hypotenuse. So we can see change in x is our opposite, and a is our hypotenuse because it's opposite to the 90-degree angle. So we'll have change in sine of theta equals change in x over a. But we also see that we have sine of theta here as well. So we can see this is also opposite over hypotenuse. The opposite will be the y min. We can see that kind of like right here, it goes that way. But we can also see, as we said earlier, it's so far away that the leg is basically equal to the hypotenuse. So the hypotenuse will also just be L. So we can put L is equal to that, and we can set these equal to each other since sine of theta is equal to sine of theta. We can just say that's change in x over a is equal to y min over L. You might be like, hold on a second, that doesn't look like the equation we used earlier. And you'd be right. Change in x is actually equal to m times lambda, because change in x, to find the bright spot, it needs to be a factor of lambda to have that constructive interference, because it's basically a cyclical motion, so to say. So we can say m of theta, we can multiply both sides by a, so we'll put a on this side, and then a times y min over L. And that's more like it. That's the formula we had before. Awesome. So that formula doesn't work because we can't, for Fresnel diffraction, if we look back at this, we can't necessarily say that the hypotenuse is equal to the leg, L, because they're not parallel anymore. You would be like, if there's a point right here, and then there's a point right here, these are obviously they're obviously intersecting. They're not approximately parallel anymore. So this relationship no longer works. And then one other thing is a slit length versus lambda. If lambda is much less than d, the fringes will get super tightly packed. This is basically because there's a formula in our formula sheet. I think it's sine of theta is equal to m times lambda over d. And, well, I guess a better would be a. A is our aperture. And then I guess D. I should have put A. I should have put A instead. So this is A. So sine of theta is equal to m lambda over A. Yeah, so if A gets supermassive, that means lambda is going to get super small, and sine of theta is just going to be a super, super small value. And say sine of theta is equal to 0. It's almost equal to 0. That would mean theta is basically equal to 0. Theta will just be so small, and the fringes will just get super tightly packed. But let's say lambda is much, much greater than 8. Then the fringes will be super spread out, and it might not even have a meaningful interference pattern. Because if I just keep choosing bigger values for sine of theta, sine is a cyclical motion, so it'll basically just keep reoccurring, and you could get a bunch of different values that it doesn't even make sense anymore. And that's it. Thank you for watching. Bye.